Welcome to this lesson on Fast Connect co-location with Oracle. So let's get started. So what is co-location with Oracle? So as you can see here, this is the Fast Connect data center location where there is Oracle cage. There are Fast Connect edge devices inside the Oracle cage. What you also see here is that the customer has a presence in the Fast Connect data center location. You can see the customer cage and you also are able to see the customer premises equipment. So all you need to do is to create a cross connect between your edge and the Fast Connect edge. So you just need to establish connectivity from your network equipment, which in this case is the customer premises equipment, to the OCI edge. And in order for you to establish this connection, you will typically hand over the letter of authorization that Oracle will provide you to the data center provider, who are then going to configure the direct cross connect. And this model or this connectivity model is suitable if you already have presence at an Oracle Fast Connect location. As you can see here, the customer premises equipment or the customer cage is already there inside this data center location. You can see this is the OCI region. This is the Fast Connect location. This is the customer data center, and this is the customer premises equipment. So in case of co-location, we just create a physical connection or we establish cross connect, which is redundant between the customer equipment and the Fast Connect edge device, which is deployed in Oracle Cage. Now let's try to understand what are the steps when it comes to configuring co-location with Oracle. So first of all, you need to set up a dynamic routing gateway in case you plan to use a private peering or a private virtual circuit. Next, you need to set up the cross connect group and the cross connect. So basically you will be creating a connection which can consist of a cross connect group, or it can also have just one cross connect. So after you set up the connection, at the Fast Connect location, you need to submit letter of authorization and request cabling for each cross connect. After that, you need to check the light levels for each cross connect, and you need to confirm that the light levels are good. You also need to confirm that the interfaces are up. Now, when the physical fiber cables in the Fast Connect location are set up and they are ready to use, then you need to activate each cross connect. After that, you can create one or more virtual circuits for your connection. The next step is configuring your edge, which means you need to configure each of your edge routers to use the BGP information for the virtual circuit. Next, you need to ping the Oracle BGP address and confirm that the BGP session is established. After that, you can test the connection. So this marks the end of this lesson. Thanks for your time. Welcome to this demonstration on Fast Connect. Let's get started. I'll take you to the OCI console where I will click on navigation menu and click on networking. Under customer connectivity, I'll click on Fast Connect. Now, as we discussed in the theory lessons, we can create a Fast Connect. And when we create a Fast Connect connection, it will ask you for the connection type, and there will be two options. The first will be Fast Connect Partner, and the second will be Fast Connect Direct. So this direct is going to include both third-party provider and the co-location. So if you click on Partner, you are provided with an option to select a partner, and depending on the region you are in, you will be able to select a partner of your choice. So you see there is Equinix. So you can see the list of partners. Let me select Equinix. I'll click on Next. So here you need to provide a name for the connection. This is your compartment. This is where you will select whether the virtual circuit is going to be private or public. So here you can select whether you want all traffic or you want only IPsec over Fast Connect traffic. That means you have an option of encryption in case of fast connect as well. Let's say you select all traffic. This is where you select the dynamic routing gateway, and this is where you configure the provisioned bandwidth. You see you have values ranging from 1 Gbps to 10 Gbps. Now this is where you need to provide your BGP IP address. This is going to be the BGP peering IP address for your edge. This can be from /28 to /31. Oracle BGP IP v4 address, this is optional. So here you need to provide the public or the private ASN for your network. So I'll not be creating this connection because this involves third party, but I just wanted to show you what all are the options. Similarly, if I click on cancel and click on create fast connect, this time I select fast connect direct, you will see that this option will disappear. So click on fast connect direct. Now in this case, you will create a connection. And after creating the cross connect, you will receive the letter of authorization. So in case of third party provider and in case of colocation, you will receive the letter of authorization. After you hand over that letter of authorization to the data center personnel, and after he completes the cabling, you will be able to activate the cross connect. So if I click on next, you see in this case, you just need to provide a name and you need to select the cross connect type, whether you need to configure a cross connect group, and you can see how many number of cross connects can you configure in a cross connect group. And you also have the option to select a single cross connect. So this is where you will specify the port speed. And this is where you will select the physical location. So this is your fast connect location. And then you will click on create. So these are the two options when it comes to creating fast connect connections. In the theory lessons, we have discussed the flow depending on the type of connectivity model. All right, this marks the end of this console walkthrough steps when it comes to creating a fast connect connection. Thanks for your time. Welcome to this lesson on fast connect redundancy best practices. Let's get started. So first, Oracle provides multiple partners for each region. Then between each Oracle partner and Oracle, there are multiple physical connections. And there is at least one fast connect location for each region. For some regions, there are more than one. And in a fast connect location, there is a minimum of 2 fast connect routers. So let's first look at the physical overview of a fast connect location. So on the right, you see the OCI region. Here you see that there are 2 fast connect locations. You are also able to see the edge devices. Similarly, in fast connect location 2, there are 2 edge devices. Now let's say there is a cross connect that you have configured that is represented by this blue line. Now in case you were to create a second cross connect, you typically go for this one in case you have multiple fast connect location. So the one marked by red line, because you want that the connection should be up even if the fast connect location 1 goes down. And if this fast connect location 2 is not available, then you'll typically go for this green dotted lines. That means you'll connect to this fast connect edge device 2. Now in case of Oracle partner, what is Oracle going to handle? First of all, it is going to handle the redundancy of physical connection between the partner and its network, the redundancy of routers in fast connect locations. As we have seen in the previous diagram, there are 2 routers in each fast connect location. Now what is the customer going to handle? The customer is going to ensure that the connection or the physical connection that it has established between the existing network to the Oracle partner network, that is actually redundant. So if you look at this fast connect partner, it comes in 2 flavors. The first is layer 2 connection, and then we have layer 3 connection. So in case of layer 2 connection, the fast connect BGP session is directly between the customer edge and Oracle. And at a minimum, each partner has two separate physical connections to Oracle. And each virtual circuit should go to a different physical router in the Fast Connect location. And you can see that this is what is happening over here. So virtual circuit 2 is on the second physical connection to Oracle. Now, in case of layer 3 connection, you can see that there is only a single virtual circuit and it is automatically redundant and diverse. Because in this case, in case of layer 3 connections, the Fast Connect BGP session is between the customer edge and the Oracle partner. And there are separate already established redundant BGP sessions between Oracle and the Oracle partner. So we just need to ensure that the connection between the customer edge and the provider is redundant and diverse. So let's now talk about the third-party provider or co-location with Oracle. In case of third-party provider or co-location, Oracle is going to handle the redundancy of the routers in the Fast Connect locations, and the customer is responsible for making the physical connection between their network and Oracle redundant. So as you can see here, in case of Fast Connect Direct, be it co-location or third-party provider, there are two virtual circuits. So you see this Fast Connect location, there are two edge devices, and then there are two virtual circuits. The first virtual circuit is on the first physical connection, and the second virtual circuit is on the second physical connection. Now, what we can also do is we can configure this site-to-site VPN as a backup of the Fast Connect. The blue one, it represents the Fast Connect private peering. The red dotted lines, they indicate the site-to-site IPsec VPN tunnel. So we can configure at least one available tunnel. We can also use ECMP across multiple tunnels for additional VPN bandwidth. In this case, the Fast Connect connection, which is represented by this blue line, is going to be preferred over VPN when the same route and routing attributes are advertised over each connections. So this marks the end of this lesson. Thanks for your time. Welcome to this lesson on transit routing. Let's get started. So first of all, let me explain you what is transit routing and why do we require transit routing. So let's suppose your organization has three departments, A, B, and C. And each of these departments have VCNs. For the sake of simplicity, we are considering one VCN per department. So VCN A, VCN B, and VCN C. And also suppose that your organization has an on-premises environment. So there is an on-premises network. And this on-premises network, it needs access to all the three VCNs. So VCN A, VCN B, and VCN C. Now, as we have already discussed in previous lessons, when it comes to connecting a VCN to an on-premises network, you have to set up either site-to-site VPN, so site-to-site VPN connection, or you have to provision a Fast Connect circuit. So do you think this is a feasible approach to have site-to-site VPN connection, either have Fast Connect or site-to-site VPN connection here, here, and here? Of course, no. So first of all, there will be increase in cost. And secondly, there is also an overhead or administration overhead of maintaining these connections. So what you typically need is you require that this on-premises network should be able to communicate with these three VCNs without having multiple site-to-site VPN or Fast Connect connections. So the answer is transit routing. So let's look at what happens in transit routing. So in case of a transit routing, you have this on-premises environment. And in the on-premises environment, there is going to be a customer premises equipment or CPE. And then we are going to have a concept of hub VCN. So this is your hub VCN. Think of it like a centralized VCN. Now what we will do, we will establish the site-to-site VPN or fast connect between the hub VCN and the on-premises environment. So this is going to be your site-to-site VPN or fast connect. Only one this time. And what you can typically do now is you can establish local peering connection. So this is, let's say, VCN1, which is your spoke. Similarly, you can have another local peering connection, which is your VCN2. This is also spoke. And let's say another one, VCN3. This is also your spoke. So this is all your local peering connection. So here you will have 3 different local peering gateways, 1, 2, and 3. Here also you will have local peering gateway. So this is what is known as your hub and spoke topology. So one VCN is acting as a hub, and in our case, there are 3 VCNs that are acting as a spoke. So this hub VCN, it connects to your on-premises network by using either site-to-site VPN or fast connect. And then the other VCNs, in our case, VCN1, VCN2, and VCN3, these 3 VCNs, they are locally peered with the hub VCN. Now, if I talk about the traffic between this on-premises network and this peered VCNs, it is going to transit through the hub VCN. And there is a condition for this scenario that all the hub as well as the spoke VCNs, they must be in the same region. So this hub VCN and the 3 spokes, they must be in the same region, but they can be in different tenancies. So this is what is known as your hub and spoke topology, and this is how transit routing is actually set up. So let's now talk about one of the architectures. It's very similar to the one that I described, but in that scenario, we will also have a look at what entries do you need to have in the route tables. So let's look at that. So first of all, I will draw this, and I need space for the route tables as well. So I am just drawing it like this. So this is going to be your on-prem. This is your on-premises environment. And this is going to be the hub VCN. And the hub VCN is going to have 10.0.0.0/16. So there is a dynamic routing gateway. And here there is a customer premises equipment. And we have established either a site-to-site VPN or fast connect connection. Now there are also 2 local peering gateways here. I am representing it by this name, LPG Hub 1. And this is your LPG Hub 2. So these are the local peering gateways. This is the dynamic routing gateway. So there are 2 spoke VCNs in this case. So this is the spoke VCN1, and this has 192.168.0.0/24. And there is another spoke VCN. This is spoke VCN2, and its CIDR is 192.168.1.0/24. And inside this, we have a subnet 2. Inside this, we have subnet 1. And inside this hub VCN, we have subnet H. There is also this local peering gateway here. I will just call it LPG1. And here it's LPG2. Okay, so this is the setup. Now I have mentioned in the previous discussion what is transit routing. So traffic from here can reach here through this hub VCN. But for that to work, you must set up VCN transit routing by creating appropriate route rules. So here we are going to look at 6 different route tables. Let's start with the route table for subnet 1. That means this particular subnet. So here, in case of subnet 1, we can have 2 rules in the route table. So if the destination is 172.16.0.0/12, what is going to be the next hop? That means from here, if the destination is on-premises network, so your next hop is going to be the local peering gateway 1. Now similarly, if this is the destination 10.0.0.0/16, then also this is going to be the next hop. Similarly, for subnet 2, 172.16.0.0/12, in this case, the next hop is going to be this local peering gateway. And even if it is 10.0.0.0/16, this is going to be your local peering gateway 2. So this is how the route table for subnet 1 and subnet 2 is going to look like. Now what about this DRG? Let's consider this as well. So in case of this DRG, if the destination is 192.168.0.0/24, what is going to be the next hop? The next hop is going to be local peering gateway H1. And similarly, 192.168.1.0/24, this is going to be the next hop, local peering gateway H2. Now, remember, this dynamic routing gateway has its own route table. We are not going to touch that particular route table. So here, what we will do, we will create a route table in the VCN, and then we will attach that route table to this particular dynamic routing gateway. And this VCN is going to be your hub VCN. And I will show you from where you can configure this in the console. So the third route table is also done. Now let's look at the route table associated with this subnet hub. That means the subnet that is deployed in the hub VCN. So for this subnet, we will have 3 route rules. First, the destination. So this is the destination, and then 192.168.0.0/24, and then 192.168.1.0/24. So here you see that from inside this, if you want to go to 172.16.0.0/12, the next hop is going to be the dynamic routing gateway. If the destination is this one, then the next hop is going to be LPG H1. 1.0/24, that means spoke VCN 2, then the next hop is going to be LPG H2. So this is also sorted. So we are done with configuration of 4 different route tables. Now the 2 entities that are left are the local peering gateways. Now this is something that you also need to understand. In the previous demonstrations, we have seen that when we create a local peering gateway, we simply provide a name and then click on create local peering gateway. But what we can also do is we can associate a route table with the local peering gateway. And I will also show you this after this whiteboarding. So how the route table is going to look like for both these local peering gateways that are attached to the hub VCN. For this local peering gateway H1, if the destination CIDR is 172.16.0.0/12, the next hop is going to be the dynamic routing gateway. Similarly, for this particular local peering gateway, LPGH2, how is the routing rule going to look like? If the destination CIDR is 172.16.0.0/12, the next hop is going to be the dynamic routing gateway. So these are the 6 route tables that you need to configure if you successfully want to implement this hub and spoke topology. Now I mentioned that I will show you two things. First of all, how to attach a VCN route table to a dynamic routing gateway. And secondly, how to attach a route table to local peering gateway. And you see that currently I am inside one of the DRGs. So in DRG, you see that it has its own route tables. And we have discussed this in great depth in the previous lessons. But now, if you go to the VCN attachment, you see this is the attachment. You click here. Now here you have to click on edit. You click on edit, you have to click on show advanced options. You see this is the dynamic routing gateway route table. And we have discussed this. The second option is what is your VCN route table. So let me click here. And you see that there is already a route table that is attached. So I have already attached. Initially it will be none. But I have already attached this particular route table. And once you have attached a route table, you can change the route table, but you cannot select none. All right, you see, it is grayed out. So this is how you can associate a VCN route table to a dynamic routing gateway. And this note also mentions that you have to use this advanced feature only if you are setting up transit routing. So click on cancel. Now I will return back to networking. Let me talk about the local peering gateway as well. So this is my VCN. You see there are no local peering gateways. So let me click on local peering gateway. I will just give it a name. Now in the previous demonstrations, what we were doing, after providing this name, we just clicked on create local peering gateway. But in this case, we will click on show advanced options. And this is where you can associate a route table with a local peering gateway. Towards the end of the discussion, I mentioned that the route table for local peering gateway for our hub VCN was having DRG. Both the route tables were having DRG as the next hop. So if I try to select any random table, for example, let's say this one, and try to create this, it will throw an error. You see, it says rules in the route table must use a dynamic routing gateway as a target. That means we have two columns, right? Destination and route target or next hop. So it must be a dynamic routing gateway or it must be a private IP. So this is what you need to understand. So this marks the end of this discussion on transit routing. Thanks for your time.
As an architect, is it must to have a hands-on experience? Well, let's try to address this question in this video. I would like to start with a small example. Let's say you want to learn how to ride a horse. Now you have two choices. Either you go ahead and read how to ride a horse, or the second option is you go and ride a horse. Well, the second one might seem challenging here because you might get hurt initially, but ultimately in the long run, you will get benefited. That means you will know how to ride a horse, right? You will exactly know what to do while riding a horse. Now, same is the case with designing cloud architecture. It might feel good knowing all the services, or 10,000 feet overview of all core constructs and different OCI services. But at the end of the day, if you have not logged into the OCI console and not tried out different things, when your customer reaches out to you, you might not be able to do justice to the job that you are doing, right? So my recommendation is log into the OCI console and get your hands dirty. Try out different combination of things that you can do inside the OCI console for a particular service. And once you do that, you will be ready to face the customer as well as address their queries, no matter however technical it is. Welcome to this module on load balancers. In OCI, there are two types of load balancers, load balancer and network load balancer. In this module, we'll talk about both these types and the use cases associated with each one of them. We'll also have a discussion around public load balancer and private load balancer. Towards the end of this module, we'll talk about a service which is known as OCI Web Application Acceleration. This service helps you speed up Layer 7 traffic over Layer 7 load balancer by using a combination of caching and compression. So let's get started.
Welcome to this lesson on load balancers. Let's get started. I'll start the discussion with whiteboarding. First of all, we will understand what a load balancer is. Say, for example, this is a client, and in the middle, there is an entity which is load balancer, and then there are different servers. Client will send the request, so you can think of it like one entry point, and then load balancer sits in between, and it is going to distribute the traffic to multiple backends. So that means here there are multiple servers or multiple backends. It load balances or distributes the incoming traffic to multiple backends. Now, what is the benefit associated with the load balancer? The first benefit is scaling. At any point of time, you can increase the number of servers. Let's say there were 3 servers, I made it 4. So you can increase the number of backend servers. So that flexibility is there in case of load balancing. The second benefit is resource utilization. So this load balancer, it is going to distribute the traffic to different backends based on load balancing policies. So it will ensure that these resources are properly utilized. So this is also one of the benefits. And the third benefit that I can think of is load balancer ensures that you get high availability. Why? Because you see there are multiple backends, multiple servers behind a load balancer. Even if one of the server becomes unhealthy, then load balancer is going to continue distributing the traffic to other servers. And that is how it ensures high availability. So now let's discuss about the types of load balancers. And we have separate lessons coming up on these types. But just to quickly explain you, there are 2 types of load balancers. The first one is public load balancer, and then we have private load balancers. As the name suggests, public load balancer is going to have a public IP, and it will be reachable from the internet. Private load balancer will have private IP, and this IP address that will be from the hosting subnet, the subnet inside which this private load balancer is going to reside. And then it is only visible from within the virtual cloud network. Now let's talk about the load balancer concepts. There are a total of 9 concepts, and I will discuss it one by one. The first concept is that of backend servers. So what is a backend server? At the very start, I mentioned that load balancer distributes the incoming traffic to multiple servers that are placed in the backend. So backend server basically means that these are the servers that will generate the content. For example, this is your load balancer. This is the incoming traffic. So it can be TCP or it can be HTTP traffic. So this is the incoming traffic, and then the load balancer is going to forward it to or distribute it to the backend server. So ultimately, this backend server is responsible for generating content. Now, the second component is backend set. Backend set is nothing. It's a logical entity. And you can think of it like a list of backend servers. For example, backend server 1, backend server 2, and along with the backend server, the health check policy as well as the load balancing policy. We are going to look at both these terms are also included. That means the backend set is defined by the list of backend servers plus the health check policy plus the load balancing policy. So this is what is your backend set. Now let's talk about health check policy. So the third construct is health check policy. Now what is this health check policy? This is simply a test. And what's the test all about? As I mentioned, we have the load balancer, we have the incoming request, then the load balancer is going to distribute it to different backends. Let's take the example of this backend server 1. Now this test is going to confirm whether this backend server is available. So if the backend server fails, then the load balancer is going to take this server out of rotation. And there are two ways in which you can conduct the health check. The first is you can conduct it at a TCP level, and the second is HTTP level. In case of TCP level, it is going to be a connection attempt, and in case of HTTP level, it is going to be a request. In case of HTTP level, the request is going to be sent at a specific URI, and then the response will be validated. But the primary purpose of health check